we will continue our discussion on space segment, particularly the bus of the satellite, and we had already discussed the attitude and orbit control system, AOCS, and then we came to telemetry, telecommand and tracking, and out of that we have covered telemetry and telecommand briefly, and we were discussing about tracking. So just recollect, we said for the tracking there is some problem we are facing, that is when we send tone, we will get a certain ambiguity in number of full cycles that has passed, which we do not know. We do not know that count. So therefore, a lower frequency tone is required so that a full cycle covers the up and down range, that is 2 times the range, but then you do not get the accuracy. So therefore, a higher frequency tone is required to get the accuracy, where the phase is smaller. So therefore, lower frequency as well as higher frequency tone both are required. This is on the tone, but nowadays in digital system we get much more precise way of doing it, that is by sending some code, that is through some technique which is called spread spectrum technique, something like that. So we have a tone which is actually digital tone, let us call it digital tone. It is based on correlation, that means certain code we send, and the receiver knows the code, the same place the transmitter is there. So transmitter sends the code, it goes to the satellite, it comes back, and then the code is compared with the transmitted code, and the delay in the code in terms of how many bits it got delayed, from that you can find out what is the range. A simple way of finding is that you have an autocorrelation signal, that is xt, and xt get delayed by tau, and the locally generated code which is already stored, when it is compared and that locally generated code, when it is shifted by the tau amount, that is in terms of delay tau amount, then you get the autocorrelation proper. Now in case of that, I have shown as a summation, it is a continuous process, but it can be digitized also. In the digitized form, let us give a simple example. Many of you know that, but still I repeat that let us say we are transmitting a code of 5 bit, which is 0 1 1 0 1, which is transmitted, and after some time we get back the code which is already shifted, that is 0 1 1 0 1 0 1 1 like that. But at this point, when we try to compare this snapshot, we find that correlation is happening only in 1 bit out of 5 bits. So only 1 bit has matched, that means code has not fully matched, so we have to delay it further. Let us delay it by 1 more bit. So this 0 1 1 0 1 0 1 1 is shifted further 1 bit. Now it becomes 0 1 1 0 1, which exactly matches with the transmitted code. This code, transmitted code, is already stored in the receiver. So with the stored register, you compare the received code and you get 5 bit match. So it is like almost like a delta function, that is our autocorrelation function is, I can call it a maximum length sequence code, that is generation we will see, and then it is like a delta function. When it matches, it gives the all match. This is the exclusive OR matching, modulo 2 addition. You can do it exclusive NOR also. How do you generate that PRBS code with a shift register? You know the technique, but still I repeat that let us say there is a 4 bit shift register A0, A1, A2, A3, and the output of A0 and A1 is modulo 2 added and fed to the A3 and shifts in the right side direction. So this side you will get the PRBS code, and so the next value of A3 will be the modulo 2 addition of A0 and A1. So like that it will continue, and it can be seen that the pattern which comes out is repeating after 15 bits, that is to the power 4 minus 1. That is, since 4 bit shift register is used, so it is the maximum length of pattern which generates, and in between the pattern the autocorrelation property, there is a property that bits are random. This can be used. One of the advantage of this, now at the bit rate you are sending, it seems that this particular pattern is much slower than the bit rate. There is 15 of such bits makes this pattern. So, it is 15 times slower than the bit rate. That means, I can get a low frequency tone as if equivalent to a low frequency, which can be used as ambiguity removal. So, by using this number of shift register and making it maximum length shift register by properly doing the modulo 2 addition, I can make the length of the pseudo random binary sequence much larger. So, that is a low frequency and which will remove the ambiguity. We can make it such larger that that range 2 times the range, it will be more than that, and then each bit of that is going at a particular bit rate, that is at a high frequency rate. So, that gives the accuracy. So, bit by bit if you do, it gives the accuracy. So, I get both low frequency, that is ambiguity removal, and I get the accuracy at a much higher frequency. So, this is the technique which is called, people call it a CDMA ranging, that PRBS, using PRBS spread spectrum ranging. This is one of the technique. It is a two-way ranging. There are some techniques where people do one-way ranging. Here we are not going to discuss that. Let us see this two-way ranging. Okay. Now, there is one more thing we should consider. We find the range, but then satellite is not stable. It is slightly drifting depending on the forces which are acting on it. So, if you remember earlier our discussion, there is a station keeping box, that within that satellite goes on drifting depending on the push and pulls which are forces which are acting on it. So, it may have east west, north south, and certain radial movement also, or a component may be there which can be radial to the center of the earth. So, that is a radial movement. Now, that means when you are trying to do the range, that time itself satellite is moving. So, moving at a particular rate, that is called range rate. So, let us try to calculate the range rate based on the uplink frequency, downlink frequency, and the radial velocity and velocity of light. Now, uplink and downlink frequencies I have already mentioned earlier. There is some allotted frequency. So, it can be put as a ratio. I will do some rough calculation. Let us see it carefully. Let us assume that downlink frequency f d and uplink frequency f u, the ratio of that is a number 240 by 221 based on the what frequency is selected. Here I have taken this particular number. You can take the exact number what on which it is being transmitted and received. So, simply from this expression we can find out downlink frequency is uplink frequency multiplied by the factor 240 by 221. Okay. Now, when I do a uplink at the satellite is moving. So, uplink frequency will have a Doppler. So, that Doppler frequency, let us term it Fu star. Fu star will be the Fu itself plus the delta Fu, which is velocity in the radial direction by c. C is the velocity of light. So, it is Fu into 1 plus Vr by c. That is the frequency which is reaching at the satellite, the original frequency plus the Doppler. Now, this plus sign depends on which direction it is moving. In this case, we have taken that it is coming towards the earth. So, it is a positive direction. Now, satellite will convert this one and repeat it down to the earth. So, it will take this frequency and put it in as a downlink frequency, and downlink frequency is uplink frequency multiplied by a factor which we have assumed 240 by 221. So, in this case downlink frequency will be 240 by 221 this factor multiplied by the uplink frequency with Doppler, that is Fu star, and which is in terms of Fu is 240 by 221 Fu multiplied by 1 plus Vr by c. Now, when this downlink frequency comes down to earth, that Doppler again is happening on it. So, on the earth station received downlink frequency will be having certain Doppler, which is again 1 plus Vr by c. So, the whole thing will be downlink frequency star, which is the downlink frequency plus the Doppler, is equal to 240 by 221 Fu into 1 plus Vr by c whole square, because 2 times it is happening. I mean, it is going up and down, so that is why multiplied. So, it is square. Now, the square means 1 plus Vr by c whole square plus 2 into Vr by c. Now, Vr radial frequency is very small compared to the velocity of light. So, therefore, we can neglect that Vr is very small compared to C. So, Vr by C whole square can be neglected. So, in this case the term will be Fd star is equal to 240 by 221 Fu into 1 plus 2 times Vr by C, right. Now, then the downlink Doppler, that is the receiver earth station is seeing, that is delta F, will be Fd star minus the downlink frequency what is supposed to be. So, it will be 240 by 221 Fu into 1 plus 2 into Vr by C minus the expected downlink frequency, which is 240 by 221 multiplied by Fu. Now, by reducing the this expression will be 240 by 221 Fu into 2 Vr by C, because the 2 Vr is there. So, the radial velocity can be expressed in terms of the Doppler and the uplink frequency, or it can be done in terms of downlink frequency and Doppler. Only this ratio will change, that factor will change. So, this is a nice expression, and from that we can find out any unknown. If the delta F is known, I can find out the radial velocity. If radial velocity is known, I can find out the expected delta F, etc., etc. Depends on Fu and Fd and their ratio. So, and of course, we have to see that radial velocity is positive or negative depending on which direction the satellite is moving. So, this is also another part of the range, which is called range rate. So, with this let us complete the discussion on telemetry tracking and command, which is very brief description. We will go into the other subsystems. Let us go into the another very important subsystem, which is power. Now, power in case of satellite will have, and common satellite, typical satellites will have two types of sources. One is the solar power, what we take. Another is when sun is not available, that is when satellite is under the shadow of earth, it is the battery power that will support, which we will call secondary power. This solar power will charge the battery, keep it. So, we will try to see how we can generate the solar power and how long, what is the size of the solar panel, etc. Let us further discuss. The energy which comes, or the solar radiation which comes to the earth, approximately average, it is estimated and calculated, and it has been found that it is roughly about 1370 watt per meter square. It is a typical number, it may not be very exact, 1370 watt per meter square, which is near earth. That is the average solar radiation which reaches. But we have to remember the earth is moving around the sun not in a exactly circular path, it has certain eccentricity. So, sometimes in the year earth is away from the sun, sometimes in the year earth is nearer to the sun. So, this radiation will be varying based on the eccentricity. The eccentricity is roughly estimated as 0.89 or 89%. So, this also factor has to be considered. When it goes away from the sun, the solar radiation which will be reaching the satellite will be smaller. We have to also assume certain things like from sun to the earth surface or earth atmosphere, whatever average solar radiation we are talking, almost it will be almost same to this particular type of satellite, which is low Earth orbit or medium Earth orbit or even geosynchronous orbit. Though from the earth surface it is 36,000 kilometer, but if you see the distance from the sun to earth is very, very large. So, we can take this number which is reaching the earth surface as same which is reaching the satellite. Now, solar cells are commonly used at present, also it is being used as silicon and or germanium gallium arsenide. It is not germanium, gallium arsenide. Now, these two will have different properties. People have experimented on that. Mostly silicons are used. Let us see the current voltage characteristics of a 2 by 2 centimeter square, the 4 centimeter square silicon solar cell. It is roughly, it goes like this, that initially at very low voltage current is constant, and then as the voltage increases, the current will fall. So, the maximum power can be attained when the voltage is about 0.5 volt, current is about 0.15 ampere. These are all typical values. So, we can set the operating point at this place. There are other problems, that is with temperature variation, this power output from the cell falls. As the temperature rises, it falls, and of course solar cells are facing a different temperature at a different time. When it's away from sun or at certain tilt angle, it will face certain different temperatures. Then the conversion efficiency is in silicon is lower, gallium arsenide is higher at a particular temperature, is normal temperature, but then gallium arsenide has more thickness and it has more mass. So therefore, before selecting gallium arsenide, that compromise has to be seen, because weight is increasing, your fuel requirement for launching that will be increasing, etc. So this is also another consideration for selection. And also one more thing happens, that cosmic particles are continuously bombarded in addition to the solar radiation, which is on the cell surface, solar cell surface. So solar cells efficiency reduces, and many times it is protected by a quartz shielding. So therefore it does not get damaged very quickly, but it's over the life its efficiency decreases. Then, as we mentioned, that power generation also varies with the variation of the distance from the sun. One more thing, that is the solar flux density depends on the nominal solar flux on Earth, similar to the satellite around the Earth. The distance factor depends on the actual and mean solar distance, also at what inclination angle it is falling. The sun is at may not be always perpendicular to the solar panel, depending on our attitude, orbit control, etc. Solar panels are also slightly adjusted, and depending on the position of the satellite, it may have certain degree, that is theta, which may not be 90 degree always. So this can be expressed in terms of solar flux density. It depends on the nominal solar flux distance multiplied with the cos of theta. Now one more thing, that solar cell efficiency, as I said, because of various reasons, it will degrade from the beginning of life to the end of life, and that depends on how much time it has it's been exposed to the sun and it's spending life in the orbit. So therefore there is another expression, it's a model which is efficiency at the end of life, EOL, is equal to efficiency at beginning of life multiplied by exponential of minus 4.43 of the time or number of years it has spent in the orbit, minus 0.43 of the number of years it has spent in the orbit, because when it is in the orbit it is facing a different type of environment. So the end of life, or as the time passes, it will be reducing. So with all these different factors, the total primary power which is coming from the solar cells can be expressed in terms of solar flux density, the conversion efficiency E. Then there is certain percentage loss due to that shielding which is done, as well as the certain shadows that might be falling onto the solar cell. The body of the satellite will, or antenna, might be creating certain shadow. So there is certain loss which is small l, and then surface area of each cell, and of course number of cells. So when this requirement of the power is known and other factors are known, we can calculate how many number of cells are required for a particular cell surface area S. I just put a very simple type of estimation which you should calculate. Find the number of cells required to generate the end of life power of 6 kilowatts. Assume that solar flux, here the number is missing. Assume the solar flux is 1219 watt per meter square. The solar cell efficiency at the end of life is 13%, and L, which is the shadow that loss due to shield, is about and shadow is 0.28, that is 28%, and the cell area is roughly 8 centimeters square. So with this we can put into that same formula, and you can do it yourself and you will find certain fractional number with the decimal points, and obviously the next higher number has to be taken as solar. And so that power generated will be slightly more than that, but it should be a integer number. You cannot put a fraction of a solar cell, a fraction number of a solar cell. So it is like this. Now there are certain more things, that is, when you put the solar cells, between the cells the wires will go. So if we try to calculate what is the solar panel size, that time we have to consider that. So out of the total area of the solar panel, a fraction will be taken by the solar cell. So that fraction is called factor, the filling factor F. So the area of the solar panel will be the cell surface, each cell surface small s, as we have seen in the last expression, and n is the number of the solar cells required. So total solar cell area, and then divide by the filling factor, that is total solar panel multiplied by the filling factor is n into s. Other way also it can be expressed. So we have got the solar panel area. Now what is the mass? The mass of the solar panel will depend on individual solar cell mass, which is small m0, multiplied by the number of solar cells, and then this solar panel area, that is S, multiplied by the mass per unit area of the structure. So with this you can get the total mass of the solar panel. So you are seeing that what we are trying to slowly go, it is what is the size of the solar panel that is required, what is the mass of the solar panel that is required, and then really for that mass how much really power we are getting. So that is the that's a quality factor, that's a specific power. The term is specific power, is power capacity at end of life divided by total mass of the solar panel. That's what you are launching, because area is not that of a concern, because on the space you have some I mean enough area to spread your wings, but here the specific power will depend on the how much mass you are launching. So the power generated or power remaining at the power generated at the end of life, I should say. So power capacity at the end of life divided by total mass of the solar panel, that is watts per kg. If the this is mass is in terms of kg, if it is in terms of grams, etc. So another small sum, find the solar panel mass and specific power assuming number of solar cells 65,000, solar cell area is 8 centimeter square, similar numbers, filling factor 0.9, unit mass per solar cell, that is 1.2 gram, careful, this is gram, and then support structure is given in kg per meter square, careful, these two units are slightly different, gram and this is kg per meter square. So per unit area is 0.6 kg per meter square, this is in meter square, and cell area is centimeter square. So there also you have to worry about the unit, and end of power requirement is 6 kilowatt, end of life power requirement is 6 kilowatt. So what is the S? What is the solar panel mass? You can calculate out of S. S is that area, and then you can find out the mass of the solar panel by the same formula we have seen earlier. What is that number? And then what is the specific power, because the end of life power requirement is given and mass you have calculated. So you can do this calculation, right? So solar panels are made with serial parallel connection, because each of the solar cell gives, you have seen that it may be fraction of a voltage, fraction of a volt, that is 0.5 volt roughly we have shown, but in the electronic circuit we may need 5 volt, 15 volt, and then we may need much more current. So therefore it's a serial parallel combinations are done. Requirement may be varying from 10 volt to 100 volt, and maybe current may be required up to 10 ampere. So the number of series connection and number of parallel connection can be found out. The required voltage divided by voltage per cell, V by Vc, or required current divided by current per cell, that is I by Ic. So number of series parallel connection can be made. But then in addition you have to provide short circuit and open circuit protection. You will be wondering why short circuit protection. Of course, your electronic circuit which the power supply is driving may get shorted, so you should have short circuit protection. due to many reasons it may get open circuit also. So, you have to have open and short circuit protection, and general power supply design is used. Diode and grouping of series connection are used to do this type of thing. Now, let us go into the secondary power consideration, that is required battery power. Let us assume is P, and the duration during which this required power has to be maintained by the battery is T, and the capacity of the battery is in ampere hour is capital C. Specific energy, that is per unit mass, is watt hour per kg, that is EM. Mean discharge voltage, as you draw the current out, the battery will have certain voltage discharge, it will reduce. So, mean discharge voltage is VD. Capital D is depth of discharge in percentage. N is the number of battery cells that is required, and eta D is the discharge efficiency. So, it can be expressed that required power multiplied by the duration on which the power is required, the PT. It depends on N into C into VD into capital D into eta D, that is watt hour. So, from that you can find out the capacity of the battery in ampere hour. C is equal to PT by NVD, D in ND. When all other parameters are known, you can find out the capacity. When the capacity requirement is known and the required power is known, then you can find out the N. This so, we start with battery capacity, and that can be expressed in terms of the required power and the time duration P and T, and capacity in ampere hour C. Specific energy per unit mass is watt hour, in watt hour per kg is EM. Mean discharge voltage VD. Depth of discharge is in percentage is capital D. N is number of battery cells. Discharge efficiency eta D. So, PT is equal to N C VD D and eta D, and from that you can find out the capacity required in terms of number of cells. So, let us look at a small sum based on the similar expression, that is for longest duration of eclipse we have seen roughly it is T is 1.2 hours, during which the battery has to support the transponders. So, P is equal to 4 kilowatt, capacity 93 watt hour, depth of discharge 80%, discharge efficiency 95%, mean discharge voltage 1.3 volt. Find the number of battery cells required. You can use the same formula. So, power bus can be regulated or unregulated. Unregulated buses are simple and reliable, but large voltage variations will be there on the bus, and regulated bus provides a constant voltage during eclipse, but complex in realization, and each circuit will draw different types of current, generate some spikes, spurious ripples on the power supply. So, though regulated bus sometimes is used, and each subsystem use their own regulator. So, with this we stop at the power subsystem. We will continue further with other subsystem. Thank you.